A free body diagram, or an FBD, is a useful picture that allows us to see all of the forces acting on an object so that we're able to analyze those forces in an effort to maybe determine an acceleration or some other unknown quantity in a problem. Let's take a look at how we draw free body diagrams in general. So we'll use a dot to represent the particle. No matter what type of object it is, that's the easiest way to do things. Arrows represent each of the forces, and so they should point away from the dot. Whether they're a push or a pull, we always point them away from the dot. And then we label them with the type of force so that, again, we sort of know what type of information to put into an equation. The length should represent approximately how big the forces are so that we can see which way the forces are pulling on the object and sort of which force wins, or if everything is balanced like it is in this particular situation. Let's take a look at a few examples. So if a book is being accelerated to the right and we know the table is rough, that gives us some hints as to what types of forces are acting. First of all objects have a mass, and so we can right away say that the gravitational force or the weight points downward on this object. Since the object doesn't actually move up or down, we know that there has to be an upward force that has the same size or same value as that downward force. That's going to be provided by the normal force, the support force from the table. Now, because it's accelerating to the right and it's being pulled by a string, we could include a tension force to the right. And then we'll also include friction, knowing that the table is rough. We're expecting friction to be in there. Notice how the right arrow and the left arrow are not the same size. This indicates that there's more force in one direction, and that's going to mean that the object accelerates. All right, now let's look at a book on a desk, but now we are pushing down on the book with our hand. Again, the object has mass, and so there's going to be a gravitational force or a weight pointed downward, mg. Because we are pushing down, we would call that an applied force, and that force should be just drawn right next to the weight force. They're separate forces, so we shouldn't combine them into just a single arrow. Okay, so what's keeping this book from falling through your desk? Well, that's the support force or the normal force exerted by the desk onto the book. Remember, that's perpendicular to the surface, so that would be straight up. And then I've tried to draw that normal force about, bigger than the weight by a little bit of an amount, trying to say that the total force down would equal the weight, or the normal force pointing up. All right, so here we're going to think about an elevator as it accelerates downward. Okay, so there's a cable supporting it. Those are the forces that we're going to include. Now, sometimes when students think about this problem, they try to put too much into it. Notice there's no mention of friction, there's no mention of a rough surface. Actually, there's no mention of a surface at all. So there wouldn't be a normal force or friction. This is pointing us towards tension. There's also no mention of some sort of outside force like a motor or anything like that in the problem. So don't put too much into the problem beyond what you can infer from the actual wording. Elevator has mass, therefore there's a gravitational force. There's our mg. What's holding that elevator up, what's exerting an upward force on it so it's not just in free fall, is a cable. So that's going to be tension. Now, because the elevator accelerates downward, we want to make sure that the down arrow is bigger than the up arrow. Again, that's going to be important later on when we're solving questions, solving problems, to help us organize our information and understand what sorts of results we expect. What we'll do with these diagrams is determine something called the net force. The net force is an overall force that takes into account which direction the forces point. So when we look at this picture, we're not going to say 27 newtons because the two forces don't work with each other, they work against each other. The net force in this case is going to be 13 newtons. That's sort of what's left over when the 7 newtons pulls against the 20 newtons. 13 newtons left over sort of to the right. Notice the symbol for net force. It's a mathematical symbol called sigma. It represents that we are summing things up, but in a special way that takes into account the direction. Okay, in this case, we have some forces to the right and some forces to the left. And so the two that point to the right, the 8 and the 22, they will work with each other, and then they're counteracted by the 4 newtons to the left. And so our net force would be a total of 30 newtons minus the 4 newtons, giving us 26 newtons to the right, because there's more overall force pointing to the right. Now what this means is that if these were forces acting on the object, it would accelerate towards the right, or if it were already moving to the left, it would begin to decelerate because there would be more force working against it. All right, this question asks us to find the normal force on this book. The book has 4 kilograms of mass. We need to use that to determine what the weight of the book is. So we'll think about on our diagram that there would be a weight force pointing down. There would also be an applied force of 8 newtons pointing down because I am pushing down on the book. And then that has to be counteracted, that has to be balanced by an upward support force. That's the surface. Anytime an object is in contact with a surface, you should think about a normal force acting. So if I want to find that normal force value, I need to know the weight of the object. That's going to be 40 newtons, 4 times 10 newtons per kilogram. And then the normal force up would equal the total amount down. So there is no net force in this case because the object isn't moving. Here's another object that's not moving. We would say that it is in equilibrium. And so we can use that fact to determine how much force must be pushing up on that one sort of back right-hand leg. We want to think about all the forces that are pushing up and all the forces that are pushing down, and we expect them to equal each other. So our up forces, we know most of them, but I'm going to leave that F as our unknown. So we have a total of 376 newtons plus some unknown F. And then downward, we have 400 newtons and 96, so 496 total newtons. And so we can just set up a quick equation where we set the up equal to the down, and then go ahead and solve for that unknown force, 120 newtons. Again, this is an object that's in equilibrium, meaning that it either remains not moving at all, or it remains moving at a constant speed. That's what equilibrium means. The motion remains constant. Here's another object that we are told is in equilibrium. So again, we just want to balance the forces out here in 2 different directions. So the forces along the left and right direction have to balance. So whatever that A force is plus 10 would have to equal 25 and 25. And then also up and down. 20 newtons and 100 newtons pointing down, and unknown B plus 112 pointing up. So B must be 8 newtons.